Hi guys. Today we will learn about the electrical circuit. Mm, yeah, we already, I already mentioned about RLC, right? Resistor, inductor, and capacitor. It's a basic component, and if we didn't understand this part, we cannot, uh, study, for the future. You know what I mean? Like generation and motor and transformer. You know what I mean? That part, if we didn't understand the circuit RLC, we cannot understand. It's really important. Okay, guys. So today we will learn about the drawing, how we draw the pager, voltage and current, depending on the load, RLC. Okay, let's move on. So, okay, I will explain to the here. So first of all, we focus on pure resistor. Okay, so pure resistor, it gotta be heater. You know what I mean? It gotta be heater, for example, because nowadays we use the LED. So this is not pure bulb. So yeah, heater is the most realistic example for pure resistor. So which means, look at that here. First of all, the result is in the pure resistor load. The result is voltage and current in phase, which means same phase, same angle. You know what I mean? So first of all, you guys need to know about voltage and current is a different dimension. We cannot compare actually, but we just wanna know it for the pager. You know what I mean? So let's see. Since as you guys this is a sine wave, right? Or it could be cosine wave. It doesn't matter. Okay. So this every single the wave has its special values. We say instantaneous value, right? Some point, but we wanna know it easily, right? So that's why we use a pager, right? Pager indicate to the magnitude and the angle, the pager, right? So that's why we use it. And there's two ways to explain to the pager. One is polar coordinate, like for example, 110 degree, or like for another example is a complex number, like 10 plus 100 J, like this, right? So yeah, first of all, yeah. So look at that here. No, look at it here. So okay, I write down. So look at that. It has its own instantaneous values, right? So we say this is a max is a peak point here. We say okay, peak point, and sine omega t. We say this is instantaneous value, but we wanna know it to the page, right? So we prepare polar coordinate because it only indicate the magnitude and the angle something, right? So that's why we prepare polar coordinate way. By the way, from the polar coordinate to the complex number and complex number to here is also fine. Okay. Yeah. So what I meant is but here's the maximum value, right? I said peak value, but here I will say RMS value. right? RMS value. So yeah, be careful about this. So guys, look at that. Here, as I said, voltage and current are in phase in the pure resistor, right? So here, I is, here, current, and voltage is here. But you can see here R resistor. I will here this black part. So as you guys remember, V equal IR Ohm's law, right? So that's why R is this time kind of just a number like 2 times, 3 times, 4 times, like a linear load. You know what I mean? In the pure resistor. But here's you can see different. What is different? Look at that. Here's Z. We say impedance because now we are learning about AC also, right? This is just okay. This is this straight, right? But AC is this sine waveform, right? Okay, let's move on. Okay, so impedance is we use in the AC, but actually it is included by resistor plus reactance. So reactance means you guys never heard about it. So first of all, I will explain a little bit more easily. Okay, here's money. Okay, for example, this is money, right? For example, I gave it to him, and he used it, or he he used it or he lost it. By the way, the money is actually gone. Okay, whatever happened, use it or lost it, whatever happened, it's money is gone. So we say this is active power. Active power. So it's actually, actual loss or actual use. Yes, this part is the real part. And this part, reactive, we say, I gave you money, but you didn't use it. Oh, I don't need it. I just stored it. And whatever happened, the result is come back to him. Okay, not using. So there is no actual, UCC or no actual loss. Okay, so we say this is a reactive power. Got it? And combine the two of them is we say impedance. But now in this case is we have only real part, this actual, active power, and this is the reactive power. We say this is imaginary. I will explain more about it. Okay. So look at that. So since we use a pure resistor, right? So I said first of all we will draw. So since we use a voltage source system, so this is standard. Okay. So I prefer to draw with a voltage burst. So V is here, and I is also same in phase, right? This is a phase. And look at that. Jet impedance is IV, but we could do it to the polar coordinate, which means jet 0, right? So look at it here. This is real, this is imaginary. J minus J. If you guys don't know about this, don't worry about it. Just being familiar about this part, okay? I will explain more about it later, okay? Don't worry about it. So now Z is here. Z is here, right? Goes 0, right? Here. So we say this is we only have in the pure resistor, we only has a R. Yeah. So real part. So it gotta be by the loss of heat, or it should be like a actual use. You know what I mean? So for example, what about it? So look at that. Since I said in page, right? So okay. So this is a V and this is a I will say, okay? The power equal VI, right? So look at that. Here plus plus, right? Here minus minus, which means multiplies, this. And here's also plus. So which means we say this is active power. You know what I mean? Actual use. It gotta be a loss of by the heat, or it could be actual usage. Okay. Yeah. So yeah, that's it. This part. Let's move on more to the psychiatry. So yeah, here look at that. You guys can see plus plus is make a power here, right? So actually, it's gotta be spent. Whatever happened, okay, it's gone. Actual power is here, right? So let's move on. So this time we will about pure inductive load. It should be simply coil. Okay, let's see more, guys. So pure inductive load, we say just coil, for example. Okay. So what happened here? Look at that. This equation, it's really important. So if you guys didn't understand what I'm saying now, just try to see the Lenz's law and Faraday's law. I explained deeply about it. So look at that. Simply, this meaning is time goes by. If the current I is changed, the voltage is induced. It's Lenz's Faraday's law, right? So look at that. This is a core, right? First of all, in the DC, time goes by, the current is straight, no change, right? So that's why we say in the DC circuit, the coil is gonna be kind of short, nothing, happened. But in the AC, look at that. Time goes by, it changes the value. That's why V is induced. But look at that here. This is, for example, coil. If the flux is coming here, but because of the inertia, it make it another, flux, magnetic field. So it prevented the current. So that's why we say this is reactive. Okay? I'll explain more about it. Don't worry. Yeah, if you guys didn't understand, it's fine. Okay. So yeah, first of all, look at that. And we will do this equation to differential. Look at that. So dt d it gotta be j omega if we do differential. And look at that. For example, here we know about the sine. Okay, for example, it no vt vt v sine omega t, right? So if we no, it's better to yeah, sorry about, it's better to the current is. So look at that. If we, yeah, here, vi, yeah, sorry about it. Sine omega t, right? Oh, sorry, what happened? Here, I. So what happened if we do, sorry about guys, yeah. So if we do a differential, which means it gotta be changed here, cosine, right? And omega t, omega plus just omega, right? So which means it changed the page to the, this part is gonna be a 90 degrees lead. Look at that here. So voltage is gonna be, voltage is gonna be, you know, lead than the current, as you guys can see here. If we differential, we do differential here, it gotta be 90 degrees here, gotta be a lead. So that's why look at that here. The equation is here. I put 90 degrees here. So look at that. I said before about, so I said we have a voltage is standard, right? For 0. But I is 90 degrees lagging, right? 90 degrees lagging. So I is here, minus 90. This is a pager, okay? And let's move on more. So impedance, this time is, I say, pure, right? So look at that, I minus 90, V 0, equal is Z 90. Here, look at that, Z 90. So why it happened? If it goes to here, it's a kind of a mess part, okay? If you guys didn't understand, that's fine. We will learn about math a little bit about, okay? So it gotta be impedance 9. So look at that here. Complex plane. Here is real, and here is image, right? Here's J minus J, right? And where is, yeah. This part now, 90 degree here. You can see this is, we say, jet now, right? So I said impedance is R plus reactance, right? Reactance. So we say this is a part, we say reactance. And yeah, we will do a little bit about math, a little bit more. Not actual math, don't worry about it, okay? Actually, you know, I don't like it to explain to math, but sometimes we need it. It's, you know. So we will look at this, how we get it this, okay? So as I said, dt, d gotta be j omega, right? So v, if we differential here, so v equal L j omega I, and this part is here to differential when you do it. So z is I v, right? So we will say L j omega is z, but you know, z is now, as we guys know, z is z 9. Yeah. So we will say this is, you know, now it has only reactive part. No, we don't have, right? And jx. So which means it gotta be same. So I jx means what is it? X L, yeah, J. It gotta be same. I hope you guys understand that these parts, but it doesn't matter actually. We just, you know, how do we get these values? We just, try to do it. You don't need to do that. Just this time is memorizing part is inductive is lagging the current. Okay, current is lagging, and we need to memorize this equation's meaning, right? How to make a pager. V here, I here, right? And plane, a complex plane, we could explain to this here, J. Why? Here, look at that. 90 degrees is J, right? Here. And there's no resistor, and only has a reactance. That's why. Yeah, and there's one more. Look at that. Yeah. So now it has a pager differences, right, between them, V and I. So for example, this is V, and this is I. What is it? Oh, color is almost same. I hope. So look at that. This is I, right? So kind of messy. Yeah, I wanna just explain here. Look at that. So now here's I is minus part, right? But V is plus part. So that's why I don't know. Doesn't, yeah, blue is better. Now here power here, right? Power is 3I. Look at that. And no. Sorry about it. So here is minus and here is plus, right? So that's why here power is minus part. And here plus, right? Plus. And here is minus, plus, minus, right? So that's why here. And here plus, right? So actually, this is, when you average these powers, it's gotta be 0. So I explained, because of my drawing, bad drawing skill, I'll show you the picture, okay? Don't worry. So I said the reactive power is give the money or something, but actually I stored it just, and I return it back to them. That's it. This is so actually there's nothing happened, but we need to learn about reactive power. It's a really important part. Okay, but what I meant is no actual losses happen. Okay, let's see. Oh yeah, it's better than my drawing skill. Look at the here. You can see here I V, right? This is a plus part, right? Both of them. So that's why plus. And here voltage is plus, but I is minus. That's why here minus, plus, minus. So the average value gotta be 0. Yeah, let's move on more, guys. Oh, yeah. Also, this capacitor is really important. Let's move on, guys. Okay. So, guys, first of all, capacitor. We already learned about the dielectric and the insulator, right? So if you guys didn't understand what I'm saying now, try to go back to previous lecture, okay? So capacitors, natural, property is opened, infinite. You know what I mean? The circuit is open, actually. I will say here, look at that. So if we dip, it's okay. Explain one more time. Definitely, right? So time goes by. If the voltage is changed, current is induced. This is capacitor's equation. Really important. Okay. So look at that. In the DC, the voltage is same. right? So nothing happened. But as I said, the capacitor's natural property is infinite, open circuit, right? So that's why it's gonna be opened in the DC circuit, we say. But in the AC, changes voltages, right? So that's why I is induced. But this part, they, they prevent the current, right? The DC. So that's why we say also this is reactive power. I'll explain more about it. Let's look at more. So first of all, so this time, as you can see, if we do differential, so I gotta be 90 degrees lead, because if we sine to differential, it's gotta be cosine, right? So this time look at that. Current is here, right? And voltage is here. So 90 degrees current is leading, right? But in the inductor, the current is lagging. 90 degrees, uh, uh, voltage is 90 degrees more faster. Not faster, lead, you know what I mean? So look at that here. First of all, so I said since we use a voltage source system, here's V0. This is gotta be standard, and current is 90 degrees, lead. So this is we say this we draw how we draw page, right? And let's go more over. Okay. And look at that here. And now we know I is 90 and V is 0, right? So Z, the impedance is gonna be minus degrees. So if we go to the complex plane, so look at that. I said 90 is J, right? But here it's minus. So that's why this is real, this is imaginary. So this part, now, this jet is here. Reactance is here, right? But inductor is here, right? The reactance is here. You guys remember, right? Here. So that's the differences. So let's see more, guys. So look at that here. So if we do a differential this, so it gotta be I equal to C omega J. I said dt d is omega J, right? And it gotta be V, right? But as you know here, Z equal to I to V, right? So look at that. If it's coming to here, it gotta be, yeah, because V is gonna be upper side, right? So that's why it gotta be this. Got it? And as you guys know, here's minus J. That's why it gotta be a omega J is gonna be this part minus, right? XC equal to C omega J, right? That's it. Yeah. Do I need to something? Yeah, I'm double checking. Do I need to explain more about this part? Yeah, I guess it's fine about the capacitor part. Let's move on, guys. So, but as you guys know, let's look at more with this. Guys, look at that. So actually, our circuit is RLC, right? Not pure or not pure, inductor or not pure C. Some specific time it needed, but generally it is connect, right? But our most of load is, over 60% is RL, is mainly load, RL is. We will learn about like C's, the capacitors usage, like improving the power factor. We use a capacitor. Why we need to use a capacitor? I will explain more later, okay? We don't need to know about it right now. So I said here, look at that. The R, actually, we use true power, I said, right? Actual use, or it gotta be actual lost. I gave you money, it's gone. I used or I lost. By the way, the result is it's gotta be gone. So in the electrically, it's gotta be by the heat loss. Loss is gotta be indicated by the heat, or it gotta be, we actually use is we say this jet impedance is R plus reactance, right? So this part is actual loss, and this part I explained. I gave you, I stored it. I didn't use it, I give it back, right? So this is, we say, reactive power. And yeah, the thing is, look at it, guys. So here, you guys can see I max sine omega t minus zeta, and v and sine omega t. This is, I will show you guys the page. Look at the guys. So I said the standard is v, right? V0. But I said since our load is gonna be mostly RL is mainly, right? But not actual pure L. So it gotta be minus zeta like this, right? So for example, if it's a pure L, it gotta be this, right? But since this is, not actual pure L, so we say this here, zeta, the angle is here, and this is current, right? This is our general page, you know what I mean, for voltage and current, general, loads. And here you can see, cosine here. So here is power factor. If we do a cosine zeta here, VI cosine zeta is a power factor. And here also you can see here. I'm not sure you guys can see here or not. You will say, yeah. Here is this triangle. Here is a reactive, actual active power. Here is a reactive power. So I said here R is here, real power, and reactive power is here, right? So here is the zeta. You can see here. This is impedance angle, right? Because this is impedance. Look at that, R plus JX, right? So impedance angle is also gonna be power factor, same, angle. Yeah, today is kind of, will be headache. Okay, let's, quick review a little bit, okay? Not easy today, yeah, actually. Okay, pure resistor load. You got, as I said, here, look at that. The same in page, right? VI. So R is a linear load here this time. So it gotta be like 1 times or 2 times. Got it? So this is the real part only has it, right? And second part is pure R. It's the power is actually used everything, or it's actually used, so it's gone, right? And pure inductive, I say if the time goes by, the current is changing, the voltage induced, right? But because of inertia, it prevents the current, right? That's why we say reactive. You know what I mean? So reactive power, we prevent something, right? So impedance, you guys remember, right? So since we do a differential here, so I is lagging, right? Voltage is lead, right? Voltage is here, voltage is here, right? Lead, and current is lagging, right? Phasor is standard is V, voltage source system, right? V0 and I is 90 degree here, right? Minus 90. But this is, we say, power, complex plane. We could, draw this part, right? And reactive power, I said, store it and turn it back, right? And pure capacitor, I said, this is when time goes by, voltage is changing, I is, coming through. But I said the capacitor's pure property is natural property is opened, right? So that's why it's a prevent current. So it's a reactive, right? Prevent. So it gotta be a jet impedance also. But this time is I is leading, right? I is current is leading, voltage is lagging. So I is 90 degrees more lead, right? Than voltage. This is we explain to the plane, a complex planes. So yeah, I explained. And since I said we have RLC circuits, but RL mostly we use motor, RL loaders like a motor something, right? So that's why the current is gonna be kind of not straight, not pure inductive current, right? Like this angle, right? And between voltage and this is volt, right? This is current. So between this angle, it gotta be, if we do cosine, it's gotta be power factor. While impedance, the angle is gotta be also same, right? There's a true power and reactive power. We learned about, right? Yeah, that's our today's lecture, guys.